is by Professor Sankalpa Ghosh. He's from IIT Delhi, and he's going to be telling us about Moiré fractals in Twistronics.
Okay, so first let me start by thanking Indian Academy of Sciences and the organizers for kindly inviting me, and particularly my good friend Professor Manish Jain, who arranged this and approached me to give this talk. And so it's a great opportunity to share this interesting results, which is mostly the work of my PhD student Dipanshu Agarwal, who will be soon submitting his thesis, and the co-supervisor Professor Rohit Narula, who is my colleague in the physics department of IIT Delhi. And this is the talk will be primarily based on the first paper and also the initial part, where I am going to provide some background that will be on a review article which we have authored in the last year. So with this brief introduction, let me start. So this is my group in IIT Delhi. We are taking some ice creams in some local shop, and this is Dipanshu, who is the main architect of this work, and some of my other students who are also working on the various aspects of quantum condensed matter theory. And these are the, so there are some more works by another student, Disha Arora, which I am not going to discuss in this particular symposium. And these are the funding agencies, including the IIT Delhi, who keeps us going. So I will start from something very simple, given the very cross-disciplinary nature of the audience. So this is what we first start with in a solid state physics book. We study about the band structure, which is a consequence of the famous Bloch theorem, where we consider the motion of a quantum mechanical particle in a periodic potential, and this gives us the energy bands, and this essentially tells us why material exists in the three different forms as far as their conduction property exists: metal, insulator, and semiconductor. So by this band theory, essentially all solid state materials are quantum materials, because nowadays we use this term very often for sometimes for slightly different purposes, but from the transport angle, all materials are essentially quantum material, because without quantum mechanics you cannot even distinguish between the various things like metal, insulator, and the semiconductor. And but this very nice and simple physics at the single particle quantum mechanics level, that becomes very murky when you actually look at the real solid state material. And here this very interesting term, which is called the dirty solid state material. So for a long period of time, experimentalists were trying to develop a sort of model system where the ideal behavior of such single particle level solid state material can be seen. And one of the places where one can realize, so this has started in the 90s and then proceeded onwards, that in the ultra cold atomic system, where we put neutral atoms in the presence of the laser light, which creates some artificial crystalline structure of the light, and you consider the motion of these ultra cold atoms at nano Kelvin temperature. So it's a purely quantum material, and you can see this particular band structure, for example. Okay, but this is something like hijacking the solid state physics agenda from the solid state physics itself. So there is a very big discovery in 2006. So these two gentlemen, Andrei Geim and Kostya Novoselov, and also almost at the same time Philip Kim in the University of Columbia, they basically discovered the graphene. And this is a very remarkable discovery in the field of the material science, because if you look at this graphite, which has a layered structure, and that has been studied for a very long period of time, but taking out one single layer was really a mother of all discovery in the material science, and that sort of leads to a huge amount of work subsequently in the domain of the science, technology, and the engineering. And the thing which we are going to talk about in this current presentation, that is a consequence of that. So we already know that two dimension is very interesting, because in 1979 Linus and Mirheim told us that this the quantum statistics which we learn at the fundamental level quantum mechanics course, that becomes very unique when you go to from the 3 dimension to the 2 dimension. And in that particular line, various things came. So these people got their Nobel Prize, von Klitzing for the discovery of the integer quantum Hall effect, and Stormer, Sui, and Bob Laughlin for explaining this fractional quantum Hall effect. And around almost at the same time, slightly before the discovery of the quantum Hall effect, Douglas Hofstadter told us very unique feature of the energy spectrum when you combine these property of electrons in a magnetic field and electron in a lattice potential. They give a very interesting spectrum which is called Hofstadter butterfly, which has self-similar fractal structure, and there are a lot of research both in mathematics, physics with that, and that was also almost means in the last 1 decade that was experimentally realized. So we already know very interesting properties which happens in the 2 dimensions. So what Geim and Novoselov does, they actually provide us an ideal 2-dimensional system in a layer form. And once they provide that, you already know the pathways from there. You can now, as Professor Mahadevan already pointed out, that you can now put these 2 layers of similar or dissimilar materials on the top of each other, and these are what is known as the van der Waals heterostructure. So graphene discovery is, as I just written in the last line here, is a tectonic shift in the material processing, and that sort of changes many things in the condensed matter by providing us and making the dirty condensed matter system almost something like an ideal condensed matter system. And in that line, the Moiré pattern comes, and this is a very simple demonstration of the Moiré patterns. As the previous speaker pointed out, you can see it everywhere. It is a late entry in the condensed matter domain because to the people in the optics and the textile technology particularly, it was known for a very long period of time. So you can see this, various regular lattice pattern. If you put on the top of each other, you either translate or you rotate them, you get this beautiful periodicity, which is much larger. So this creates a periodicity which is much larger than the original periodicity, and if you look at any of this pattern, you can immediately figure out. So the characteristic Moiré length scales are the periods of this overlaid pattern. Now what will happen when you are going to adopt this particular idea in the material science, and that is the surprise which is coming to us for the last few years, as the coordinator of this session, Professor Manish Jain, at the very beginning pointed out. So you see these Moiré patterns all where, so that's why I told it's a late entry in the condensed matter. You see in the silk sarees, you see in the shards, you see in this X-ray plate, you see in the building architecture, in the various places you see these Moiré patterns, radiology, optics, and all these things. They are already familiar with the Moiré pattern. And this is what is happening when it comes to the material science. So I'm going to talk about a much simpler system, graphene. So this is the graphene, it's the hexagonal lattice with a lattice constant 0.246 nanometer. And when you put 2 such graphenes on the top of each other and you rotate them, then you get this corresponding Moiré pattern. So this is the Moiré pattern. And the interesting thing which happens, that this wavelength associated with this Moiré lattice, that is much larger than the original lattice. So in this particular plot, it was plotted that what is the ratio of this wavelength with respect to the original lattice constant of the graphene. You can see it's very, very large. So you essentially can tune the band structure of the entire condensed matter system by going to a much larger lattice spacing, and that's what happens in the case. And now we already know from our solid state physics that we typically like to study the properties of what is known as the quasi-particles, because it is only the electrons' behavior near the Fermi level that is very important, and that particular thing can be written in the form of a dispersion, the relation between the energy and the Bloch momentum. And now if you would like to expose those particular quasi-particles to some potential which varies over a length scale which is much larger than the typical periodicity of the lattice, then you can actually write an effective Hamiltonian. And even though all these things are highly non-relativistic, but this particular dispersion which appears here, that can be of the various form. It could be non-relativistic, it could be ultra-relativistic, it could be flat, and the various things, and accordingly you are going to get a large number of simulated materials from a basic condensed matter material. So that is one of the reasons why the graphene and the successive things that make our life both more complex as well as more interesting in terms of offering us very novel type of quantum materials in this particular domain. So the first instance is this very interesting work which was done in experiment, and then there is a subsequent beautiful theory paper in 2013 where they considered the graphene over the hexagonal boron nitride. They are both having the hexagonal lattice structure, but there is a slight lattice mismatch. So if you put graphene on the hexagonal boron nitride, it creates the Moiré. So that is the first Moiré. And a very simple way to understand this, that you can now consider these graphene quasi-particles, they are in the presence of a large Moiré lattice which is providing a periodic potential, and that periodic potential's periodicity is given by this Moiré lattice length, and this particular model was proposed in this very famous and very well cited paper in this field, which is actually tells us the first way that how to analyze this particular system. And this experiment was done in the Pablo Herrero and other, I think, I don't exactly remember who are the other authors, in a very big, beautiful experimental paper. And what they figured out that the various experimental features like this density of states, location of the Van Hove singulate and other things, that can be very well explained even if you consider just this very simple one particle Hamiltonian, which just consider the massless Dirac fermion Hamiltonian of the graphene, which has an ultra relativistic dispersion. So this is just the Dirac equation in the 2 dimension when this effective mass goes to 0, and plus a periodic potential which is created by this corresponding Moiré pattern. With this you can actually explain many features of this particular remarkable experiment. And we have basically taken this line of analysis that where we try to understand this whole subject of the Twistronics by considering, of course it's not as simple as that, there are many other caveats here, but to understand it at a very basic level, we wanted to understand these things as you consider these massless Dirac fermions in the presence of various types of superlattice potentials and try to see if using that can you understand the flat bands in the twisted bilayer graphene and so on and so forth. So I summarize this particular result in these following slides by pointing out that, so this is the graphene, you can expose it various types of such superlattice potential. So this is bare graphene, this is graphene plus some 2D muffin tin type of potential, this is graphene plus hexagonal boron nitride, this is twisted bilayer graphene, this is twisted bilayer graphene at the magic angle, this is super Moiré pattern where graphene encapsulated by 2 hexagonal boron nitride, this is a bilayer graphene encapsulated by hexagonal boron nitride. Where we more or less understand the basic single particle level physics here, even starting from here and here, there are still issues with the single particle level physics. And of course, when you come to the super Moiré structure, the single particle physics even become much more complicated. And somewhere here, our Moiré fractal, which I am going to introduce in next few slides, that is going to lie somewhere here. So that is what I am going to talk about. Okay, so this is what happens in the case of the Moiré. So you make a much larger lattice, and so your supercell size grows. And as a result, you have the corresponding smaller mini Brillouin zones, and these mini Brillouin zones are basically given by the shift between the 2 Dirac cones, and they are going to form the corresponding sides of this unit cell in the case space. So that is how we typically analyze such Moiré structure, and it is from this basic structure all the subsequent magics in the twisted bilayer graphenes and all other things that arises. And there are beautiful works in this particular direction, and particularly this work by Bissirger and MacDonald, they first predicted this flat band, and then in 2018 they have observed this very nice superconductivity and this correlated insulator state in this system which sort of set the ball rolling. And then there are series of experiments. So this is the first experiment in 2018 in MIT group. Then there are experiments in Corridin's group where they seen more complex superconducting systems and the correlated interact system. Then there are this interesting work by Ivan Rey's group successively, which is Charn insulators, Van Hove singularities, and topological flat bands in such system. And then also there are, so this is just a subset, this doesn't exhaust the list. There are beautiful work by our colleagues in the Bengaluru IASc, Anindo and Ovigbid and Arindam means they did some very interesting work on such twisted system which are not even put here. So, and of course in abroad there are many other groups which are working and getting fantastic results, particularly with the realization of something called fractional Charn insulator states in such twisted material. The things even became more interesting, which is showing us very new topological system. So we will now directly come to the super Moiré. So super Moiré, when you add 2 Moirés on the top of each other and you have to match them at some commensurate angle, and that gives you even a larger corresponding lattice constant. So the super Moiré strength is going to be, so you now consider something like in graphene, 2 hexagonal boron nitride, the top one form 1 Moiré, the bottom one form another Moiré, and together they form something like the super Moiré, and the corresponding super Moiré periodicity is much larger than the individual Moiré periodicity. So this is a typical portrait of such super Moiré structure when you put such 3 layers on the top of each other and relatively rotating them. And there are various parameters by which you characterize such super Moiré structure. So the question is, so this is another example of that. So the question is, how do I analyze such things? Well, so let's go to this very simple graphene plus hexagonal boron nitride. You can consider the graphene plus hexagonal boron nitride. If I now write this particular Hamiltonian symbolically, basic this effective Hamiltonian for the graphene under the ambient condition, which is massless Dirac fermions, plus whatever potential it is coming from this hexagonal boron nitride layer, right? So now people have analyzed this particular problem, so I am just not giving you all the technical details here, and they figured out that this particular potential can be written in the following form. So there is some effective potential here, this is some effective magnetic field, and there is some other effective term which breaks the so-called inversion symmetry, which tells these two atoms in the unit cell of the graphene, they are going to face now different potential. All these particular terms has one common property, they are all having the corresponding Moiré periodicity. So that is why you can sort of study this particular problem in this way by graphene quasi-particles in some Moiré periodic potential. And they have so now if you go to a super Moiré structure, then you have the following thing. So you have now one graphene and the two this hexagonal boron nitride, so you can just repeat this particular structure. So when you do this, you get this particular Hamiltonian which gives you the quasi-particles of the graphene and the quasi-particles of the hexagonal boron nitride, plus this one which is because of this interaction between the graphene and the hexagonal boron nitride layer. So you simplify it further by integrating out the degrees of freedom from the hexagonal boron nitride. You now get, instead of one, at the leading order you get one type of potential, you get two type of periodic potential. So this is a very simple way of looking at the super Moiré structure of a graphene encapsulated by the hexagonal boron nitride. Now you can do, of course, numerics, DFT or any other ab initio method or anything like that. But what we have just wanted to point out that these two potentials, so we have plotted this, and if you plot these particular things, you will see they are both having the periodicity, they are two Moiré potentials and they are having the different periodicity. Well, one can of course do numerics and learn many things out of these things, and the previous speaker has already pointed out in a different material how such things are analyzed using the computational technique. What we wanted to point out that there is a line in this particular space of these two angles of the rotation of this upper two layer and the lower two layer. So this line is where these two angles are exactly same in the magnitude and opposite in the sign, and along that line actually you do something analytic. So this is a line in this particular parameter space, and that analytical thing is what is we are going to propose as the Moiré fractal. And why it is so? The reason is very simple. Consider a simple, twisted bilayer graphene Hamiltonian which forms a Moiré pattern, and then just add a simple another periodic potential which has the same periodicity as the Moiré potential. Nothing interesting happens, only the conduction and the valence band they get shifted. People have analyzed this particular problem in these two papers. So to make the things more interesting, let us try to do the following. We consider again a Moiré potential having the same periodicity, but we rotate this as compared to the original structure. The moment you do this, now there is no common periodicity. The incommensuration sets in. And we would like to have some incommensuration, because we know that if there is an incommensuration in the quantum mechanical system, it actually provides a lot of interesting things. So in this case, we are also going to see what it does. So to restore this particular periodicity, what we have to do, we have to basically rotate the system in certain specific angles, and these are commensurate angles. And when you do, you restore the periodicity, but now you got a supercell again, which is going to be much larger. So this is the same technique by which people analyze the twisted bilayer graphene. We are just now repeating this particular technique by considering the twisted bilayer graphene in some type of periodic potential to understand the basic structure of the super Moiré. So you can solve some algebraic equations. So this essentially gives you some Diophantine equations which are known almost for 2000 years, and a very interesting topic in number theory, because there is no general way of solving the Diophantine equation, but in specific case the solution exists. In this case you get some quadratic Diophantine equation, and you can solve them, you can get the solutions in terms of these integer numbers. So these are the commensurate angles. So one is for a triangular lattice, another for a square lattice. You can do for any of these cases. We are interested in the hexagonal, which is a sort of triangular lattice, and we can solve this particular problem. So when you do that, you essentially get something like this Moiré fractal. So you get a repetitive structure. So the mini Brillouin which forms as a result of the formation of the larger supercell, their edges exactly fits into the older Brillouin. So this is what gives you a very repetitive structure, and this is what is Moiré fractal. So we now model this particular system. We can tell that okay, we have this system, and we add some type of sequential periodic potentials at every stage. We rotate these periodic potentials, and at certain commensurate angle, they are going to form again a commensurate structure. Then you repeat this particular thing, you get an iterated fractal, which is very well known in the fractal literature. These are known as the attractors. So this is this thing which happens in the case of the real space. So this you can immediately see that it is going to form larger and larger supercell, and as a consequence of that, it is going to form smaller and smaller mini Brillouin. And when you look at these edges of this Brillouin, you can immediately see they exactly fit into the older structure, giving the self-similarity of the fractal. Of course, in this case, if you look at this Cauchy sequence, which gives you the relative ratio of the length of these particular arms in the K space with successive iterations, that saturates very fast. But nevertheless, even within the first couple of iterations, you can already see the fractal property. But as I am going to explain it to you, it is interesting to the condensed matter community for a different purpose, because it provides us a very useful way of calculating the number of extra bands which are coming into the system in terms of the fractal dimension. So I just, means for a demonstration, I have just provided a very simple example of such iterated fractal which are available in the textbook, like Koch snowflake, and you can immediately see one can also calculate the fractal dimension. And in this case of the Moiré fractal, also we can calculate the similar dimension, and this is the corresponding fractal generators, which are known as some affine characters and things like that in the mathematics literature. So I am not using many terminologies here, but one can calculate for each of these constructions this thing very easily. But why should a condensed matter person will be interested in that? The reason a condensed matter person will be interested then, because I know the exact number of these such Brillouins which are fitted, which is going to give me this fractal structure. And once I do that, because you see, you can do this thing actually for any angle. But what we will find out that when it is not going to be a Moiré fractal, which means the angles are not going to be same, this fitting is not going to happen exactly. There will be some approximately, it will be very similar, but it will be different from this one. But here, because this particular fitting of these edges of the Brillouin happen exactly, you can actually calculate this number of bands which will now be lying within the lowest two bands in this particular system, and this can be given by this particular formula. So that is one of the main findings in our work, where we pointed out this, because if the number of bands exist, many of the other properties can be changed, and that can be calculated. So that could be one of the ways of detecting such Moiré fractal in a condensed matter system. So we then calculated using this particular formalism, and for such specific angles, we calculated the corresponding we evaluated this Hamiltonian for this tri-layer system and graphene, quadrilayer graphene, and also graphene encapsulated by hexagonal boron nitride. And we figure out in all these cases to the leading order, it is either a Moiré fractal or a Moiré fractal which is weakly perturbed for such set of these angles. And one can actually count the number of bands exactly by this particular formula which I have just provided here. Okay, so now these are all fine. So nice formula and everything there, but an experimental is asked that how we are going to see this in an experiment. So since my time is almost running out, I will now just show you very briefly. So this is a work in progress. So we are also in touch with some experimentalists. I have interesting discussion with Sankalpa Ghosh at some particular point of time. He gave us some shows us some interesting results. We are also still looking at that, and I also talked to some experimentalists abroad. So particularly with Ivan. So they have suggested something, and on the basis of that, we are now doing some further analysis. So the basic physics is very simple. So let's look at this, this band structure by putting in the third axis the single particle spectral weight. It looks like this, and one can immediately see that the spectra one can look at this particular Bragg gaps in this particular system. The same thing can be done here. Now, to find out such Bragg gaps in this system, you actually need to resort to a very complicated formula where you can write your area of the quasi-Brillouin in terms of the original Brillouin, and that also gives you a set of complicated Diophantine equation. But in this case, since you already know what is the number of bands which will be lying within your lowest two bands, you can actually look for where this particular Bragg gap comes which satisfy the Moiré fractal criteria, and then using that, you can actually in your momentum space trace this particular mini Brillouin. So we have done something on that. So here, as I just pointed out, this is a ongoing work. So I am just showing a very brief outline of this particular thing, and that may be one way to detect this Moiré fractal, because one can look at this spectral function through the RPS type of measurements, and that may be one way of try to locate such Moiré fractal. So with this, and thanking my organizers and the collaborators again, so I put this summary, so I am not reading it again, and let me conclude this talk. Thank you for your attention.
Okay, time for some questions.
So your fractal is actually terminated fractal, or it's actually infinite, full,
Well, so the Cauchy sequence that converges very fast.
No, you're saying you have an infinite number of fractal steps in your Poulin zone, or it's like does it get terminated after a finite number of iterations?
So it converges very fast. So that is why I use this particular term, that it means because the number which becomes after that becomes sort of unphysical, because you cannot really get up these things at that number. So one has to locate these things, one has to look at the first couple of iterations or things like that. So this is, for example, a very different fractal than what one finds out in the Hofstadter butterfly energy spectrum. It is not the same thing. So you are going to ask me something like that. Yeah, that is what it is. So it is not the... Yeah, Hofstadter butterfly is a very different type of fractal. Yeah.
You were mentioning at the end the comparison to experimental data. Are these done with 4 layers or more?
Okay, so at this moment you see, so this is a toy model. Okay, so we have just seen that and as I just pointed out, that these are valid only at certain specific angle of rotations. So at those value of the rotations, which you can call as an equal angle rotation, we have checked out that at least several super Moiré structure to the leading order, they are either Moiré fractal or Moiré fractal parted by weak perturbation, which has the same periodicity as the Moiré. So they do not change some property of the band structure fundamentally.
It means that there is no dependence on the number of layers?
Yes, of course, if you have a more number of layers, then of course certain things are going to change there. But we are considering, let's say if you have the the graphene encapsulated by the hexagonal boron nitride, then you have an upper Moiré and you have a lower Moiré, so you are considering a super Moiré out of that. But on the other hand, if you have an bilayer graphene encapsulated by the boron nitride, then you have to look it accordingly, so you have to decide that which is going to be a primary Moiré, and you are considering the super Moiré out of that. And so that way it can go up to a, in it's very large sequence. So those properties are definitely, so those numbers and other things are going to change according to that. But in all these cases, I can calculate the number of bands using this particular formula. That is what I am trying to point out.
Thank you.
Yeah.
Let's thank the speaker once again.